Okay, the last thing we want to talk about here in section 2.3 is a very important theorem called the intermediate value theorem. And if you read this sentence that I have typed on the notes, it's going to sound a little complicated, but I promise you the idea of this theorem is really straightforward and I hope will make a lot of sense to you. So I'm just going to point out a couple of key aspects to this particular theorem. So the first one is that f has to be a continuous function. If f is not a continuous function, then we are not able to use the intermediate value theorem. And the good news for us is that every polynomial is everywhere continuous. And so we're not going to have to worry about any of the problems in this section not being continuous. But just know that moving forward, as you get into calculus, you're going to have this, this condition that the function you're dealing with is continuous. And k has to be any number between f of a and f of b. And I want you to notice that f of a and f of b are both y values. And so that's very important. K, therefore, is also a y value whenever we talk about this sentence. If those two things are true, then there is at least one number c in the interval from a to b such that f of c is equal to k. And so I'm going to give you an example in the real world of how this theorem could be applied, and then I'm going to draw a picture for you which hopefully will make it make sense. So here's my real world example. We're in the hottest part of the year right now. This is Texas, and it gets really hot. And so let's just say that when I woke up this morning, which I woke up at about 6 o'clock in the morning, I know that's crazy, but it's the truth. I woke up at about 6 o'clock. Let's just say that it was already 84 degrees when I woke up this morning. Now, right now, I'm recording this at 1 o'clock in the afternoon. And looking at my Apple Watch, it is now 97 degrees. And so I'm just going to ask you a couple of questions here, and I want to see if you can answer them. If it was 84 degrees this morning when I woke up at 6, and it's 97 degrees now, did there have to be a time somewhere between 6 o'clock in the morning and 1 o'clock in the afternoon where the temperature was 88 degrees? Well, hopefully you said yes, because temperature can't just skip from 84 degrees to 97 degrees, can it? You have to pass through every value in between, or another way to say that, every intermediate value between 84 and 97. And notice that these would be the y values in my function, and the times would be the x values. And so another question, did the temperature have to be 96 degrees at some time between 6 a.m. and 1 p.m.? Well, 96 is between 84 and 97, so the answer to that question would also be yes. What about 98 degrees? Well, now you're a little confused. The answer to this question is yes, it could have been 98 degrees, but it didn't have to be 98 degrees. The only values that it had to have been, the only temperatures that it had to have been between 6 a.m. and 1 p.m. are any temperature between 84 degrees and 97 degrees. So anything outside that range, it could have been that temperature, but it didn't have to be that temperature. And so hopefully that real world example makes a little bit of sense to you. I'm going to show you a picture here also that hopefully will cement this. So let's say that I have a graph here. I'm going to say the x value here is A, the x value here is B, and then I'm going to draw 2 points here. We're going to say this has the y value f of A, and that up here I have the y value f of B, and that I'm going to have some value of k, which I'll do in a different color, that has to be between f of A and f of B. So I'll draw a horizontal line that goes across through K. And I want to ask you, is there any way to connect the points f of A and f of B where I don't cross through the red line? And some of you are going to try to get creative and do silly things like this. And I would say that, first of all, That's not a function because it doesn't pass the vertical line test, so you can't just, circumvent the red line by trying to go around the part that I haven't drawn. By the way, I could draw this all the way across the screen if I wanted to. And then others of you may try to get creative and do something like this, and I'll do this in green and then erase it here in a second. You might try to go, okay, well, I'm going to go here, and then I'm just going to hop over it, and then go like that. But the problem with that is that you didn't draw a continuous function. You picked up your pencil in order to draw that green line. And so that cannot satisfy the intermediate value theorem either. And so the point of this is that you cannot draw a function that's continuous that does not pass through k at some point. So you've got to have some point there where you pass through k, and the x-coordinate, according to the sentence, is called c. And notice that c is somewhere between a and b, just like the theorem said. So hopefully that picture makes sense. If not, hopefully the real-world example makes sense. But if there's something that I can do to make that more clear for you, please let me know. Okay, these last two examples are going to demonstrate how we would apply the intermediate value theorem to prove that certain functions have values that exist. And so this function, or this example, says show that f of x is equal to 0 has at least one solution in this interval if the function f of x is equal to x cubed minus x. Now, if we wanted to do this rigorously, and we do, then the first thing we want to do is state that f is a continuous function on the closed interval from -2 to 2. And that is a true statement because f of x is a polynomial, and as I mentioned earlier, polynomials are continuous everywhere. So I didn't say anything that was false here in number 1. I definitely need to state this in order to be able to use the intermediate value theorem. The second thing that we want to do is we want to find the y values at each of these two endpoints, -2 and 2. And so what I'm going to do is I'm just going to evaluate the function at the left endpoint, f of -2. And so I'm going to plug that into the function, -2 cubed minus -2. And just doing some basic arithmetic here, I believe this is going to be -6. And then I am going to evaluate f of +2, that other endpoint, and that's going to be 2 cubed minus 2, and so that's going to equal to +6. Now, I wanted to show that f of x has to equal 0 at least once in this interval. So the question now that I need to answer is, does 0 fall between these two y values? And clearly the answer to that is yes. And so what I can say is that f of -2 is less than 0, which is less than f of 2. And that's my mathematical way of saying that 0, which is the value that I'm trying to prove here in this particular problem, that's not always going to be 0, but in this particular case it is, since I'm trying to show that f of x is equal to 0, that 0 is between the y values at my two endpoints. And so you could write it that way, or you could write it this way. And so the thing that I'm going to do lastly is just basically write my conclusion statement. So if you've never seen this symbol here, this just means therefore, and I'm going to say there exists a C. And where does that C have to be located? It has to be located on the open interval somewhere between the x values -2 and 2, such that f of that C has to equal to 0, and then this is due to the intermediate value theorem, which you can abbreviate as IVT. Okay, example 9 has a very AP flavor to it, and so what I mean by that is that this is very similar to a problem that you could see on the AP calculus test in testing intermediate value theorem. So it says a car travels on a straight track. During the time interval from 0 to 60, the car's velocity, measured in feet per second, is a continuous function, and that's very important whenever we want to use intermediate value theorem. We need to be working with a continuous function. The table above shows selected values of the velocity v of t. from 0 to 60, must there be a time t? Now that language right there, I'm just going to try to train you up early here. That language is what you should look for and then think, should I use intermediate value theorem here? And so let's look here. Is there a time when v of t has to equal to -5? Well, if we look at our table, does -5 have to be somewhere on the table? Well, if you look there, -5 is not between those numbers. If you look there, -5 is not between those numbers. There, no. There, no. Here on this subinterval, v of t has to equal -5 for two reasons. V is a continuous function and -5 is between -10 and 0. And so for those two reasons, and I'm going to write them very clearly, there must be a time when v of t is equal to -5. So here's what I'm going to say. V of t is a continuous function. And I'm going to say very specifically here on the closed interval from 35 to 50. Those are my two x values on that little sub-interval right there. Secondly, v of 35 is equal to -10, as you can see from the table. And v of 50 is equal to 0. And -10 is less than -5 is less than 0. Or another way to write that is you could say that v of 35 is less than -5, which is less than v of 50. And so because of those two facts, I can state, therefore, v of t must equal to -5. And I'm just writing my sentence a little differently here. You could write it the way I did on example 8 if you wanted to. It wouldn't really matter how you do this. 35 is less than c is less than 50. Those are my two x values of my subinterval. And then I'm going to say due to the intermediate value theorem.